Hello everyone, in this video I'll be talking about the effect of conjugation upon UV visible spectra. And my name is Fayaz and I am doing PhD in chemistry at UNSW Sydney, Australia. And this is my YouTube channel and I have uploaded more than 107 videos on my YouTube channel so far. And there are several playlists available on my YouTube channel regarding natural product chemistry, spectroscopy, retrosynthesis, NEM reactions, and other stuff. Not only this, but I have made several videos related to how to apply for PhD application, admissions and scholarships, and how to write an effective email to foreign supervisors. So these are the just highlights of my channel so far, and this channel keeps growing and growing every week, every day. Every week almost I'm adding the new video on my channel. So keep watching this channel and keep supporting the channel and keep subscribing it. Okay, let's keep sharing the link, not subscribing. If you have already subscribed, thank you so much, but if you haven't subscribed, please subscribe. And let's get back to the topic. So today the topic is the effect of conjugation upon the UV visible spectroscopy. So one more thing which I forgot to mention you guys, that in this video I'll be talking from a book that is called Introduction of Spectroscopy, written by Pavia. So this is the book that I'm following for this video. And if you want the copy of this book, PDF of this book, then please feel free to write down the email ID in the comment section below of this video. Then I'll send you the book if you don't have already. Okay, so today we are going to talk about the effect of conjugation upon UV visible spectroscopy. By the way, if you are not familiar with UV visible spectroscopy, and if you are not sure what to do with this, then I have made earlier several videos about basic concepts, instrumentation, and other stuff of UV visible spectroscopy. Please have a look at those videos first and then come back to this video. But if you are already very good at UV visible spectroscopy and just want to learn about what is the effect of conjugation upon UV visible spectrum, then let's start. Okay, so one of the best ways to bring about a bathochromic shift. So bathochromic shift is a red shift, or that means increase in the wavelength. That is called the bathochromic shift. That is called the bathochromic shift. This is the lambda and this is the increase in the lambda. Okay, shift is to increase the extent of conjugation in a double bonded system. So the reason the effect that conjugation plays is it does the bathochromic shift, or increases the extent of conjugation in double bonded system. In the presence of conjugated double bonds, the electronic energy levels of a chromophore move closer together. So in short, higher the conjugation, higher will be the wavelength. So conjugation shifts the spectrum towards the red shift, towards the higher wavelength. So in the presence of conjugated double bonds, the electronic energy levels of a chromophore move closer together. As a result, the energy required to produce a transition from an occupied electronic energy level to an unoccupied level decreases, and the wavelength of the light absorbed becomes longer. Figure 7.10 illustrates the bathochromic shift that is observed in a series of conjugated polyenes. What does polyene means? A molecule which contains number of double bonds as the length of conjugated chain is increased. Conjugation of two chromophores not only results in a bathochromic shift but increases the intensity of the absorption. These two effects are of prime importance in the use and interpretation of electronic spectra of organic molecules, because conjugation shifts the selective absorption of the isolated chromophores from a region of the spectrum that is not readily accessible to a region that is easily studied with commercially available spectrophotometers. The exact position and intensity of the absorption band of the conjugated system can be correlated with the extent of the conjugation in the system. So have a look at the effect of conjugation from this figure 7.10. There are three spectra given in this figure: spectra A, spectrum B, and spectrum C. So in spectrum A, you can see there is a shorter wavelength, and in the spectrum C there is a longer wavelength. So in spectrum B, the wavelength is not as maximum as you would expect. Now the question arises that why there is a wavelength maximum here at this area and minimum at this area. That is because of the conjugation system. If there is more conjugation, then the wavelength is shifted towards in this direction, and that shift is called red shift. And if there is no conjugation, then the wavelength shifts towards in this direction, that is called blue shift. So if you see, this is the molecule CH3 CH double bond N CH3 ultraviolet spectra of dimethyl polyenes. A is N is equals to 3, B is N is equals to 4, and C is N is equals to 5. So these are the three molecules A, B, and C. So where N is equals to 3, the spectrum is A, means there is only one double bond. When N is equals to 4, then that means there's two double bonds, and when N is equals to 5, that means there is three double bonds. So as you can see in C, there is a maximum wavelength. So the reason why we have the increase in wavelength or red shift or bathochromic shift, because of the conjugated system present in the double bond. That's why we are observing the red shift in case of compound C and compound B, but not in compound A. Okay, let's furthermore discuss this conjugation in the table 7.4. Table 7.4 depicts the effect of conjugation on electronic transitions. This is alkene, and these are the ketone. So in alkenes we have ethylene, where we have a structure of ethylene is CH2 double bond. This is the double bond, and then we have the CH2. This is ethylene, and then 1,3-butadiene. So 1,3-butadiene. This is the structure of 1,3-butadiene. This one is a 1,3-butadiene. And then 1,3,5-hexatriene. 1 2 3 4 5 6 1 2 3 1 2 3 4 5 6. So this is the 1,3,5-hexatriene, this one, as it contains 3 double bonds. That's why we are calling it. And beta carotene, which contains 11 double bonds. Now ethylene gives you a lambda max at 175 nanometer, that is a unit. And 1,3-butadiene, which contains 2 double bonds, gives you lambda max at 217. Now it's quite clear from this that conjugation increases the wavelength. The effect of conjugation results in the increase or enhancement or shift in the red shift. And we have 1,3,5-hexatriene, and the wavelength is 258. Lambda max for 1,3,5-hexatriene is 258, and for beta carotene the wavelength maximum is 465. Now that is huge. Now the concept should be clear if you are listening to me. Then what I'm trying to explain, that if there are more double bonds in conjugation, not in isolation, then their wavelength will increase and lambda max will appear at the redshift. So in ethylene, where there is only one double bond which is not in conjugation, the lambda max is 175. Whereas in beta carotene, there are 11 double bonds present and the lambda max is 465 nanometer. We have ketones. Next, let's understand the ketones. We have the acetone, which is not in any conjugation, but then we have 3-butene 2-on. Three-butene 2-on. So 1, 2, 3, 4. So 3-butene 2-on. This is acetone, first one, and this is 3-butene 2-on. There are two electronic transitions responsible for the absorption in the UV visible spectrum for acetone. One is pi to pi star, which gives peak at 189, and another is n to pi star, which gives peak at 280. Whereas in butenone, there is a pi to pi which gives you at 213 and n to pi gives you at 320. Now if you compare n pi to pi star transition, there is a red shift. So conjugated system appears at 213, whereas non-conjugated system appears at a lower wavelength. That's what I'm trying to say. And similarly for n to pi star transition, the non-conjugated system appears at 280 and conjugated system n to pi star appears at 320 nanometer. So these are the effects of conjugation that can be clearly observed in the system. Okay, so one should keep this thing in mind when doing these things, that whenever there's a conjugation, that means they are going to be exhibit higher wavelength. The effect of conjugation on alkenes. The bathochromic shift that results from an increase in the length of conjugated system implies that an increase in conjugation decreases the energy required for electronic transition. This is true and can be explained most easily by the use of molecular orbital theory, MOT. According to molecular orbital theory, the atomic p orbitals on each of the carbon atoms combine to make pi molecular orbitals. For instance, in the case of ethylene, we have two atomic p orbitals, phi1 and phi2. From these two p orbitals, we form two pi molecular orbitals, psi1 and psi2 star. By taking linear combinations, the bonding orbital psi1 results from the addition of the wave functions of the two p orbitals, and the anti-bonding orbital from psi2 star results from subtraction of these two wave functions. The new bonding orbital, a molecular orbital, has an energy lower than that of either of p orbitals. Likewise, the anti-bonding orbital has an elevated energy. Now let's discuss all of this in the figure so that you can understand it better. Notice that two atomic orbitals were combined to build the molecular orbital, and as a result, let's discuss the figure so that you can understand this, what I'm talking about. So this is the figure 7.1. This is what it has been described in the book. So this is the ethylene, C2H4. These are the hydrogens, 4 hydrogens. And this is the carbon double bond carbon, so psi1 is equals to phi1 plus phi2. This is the bonding orbital. So this is the psi1, so 1 electron up, 1 electron down, and this is pi to pi star transition, this one there, and we have atomic orbital, 2, phi2, phi1, and this is the anti-bonding orbital, psi star is equals to phi1 plus minus phi2. So this is how this formation of molecular orbitals for ethylene takes place, and this is how MOT, molecular orbital diagram, for ethylene can be drawn by using molecular orbital theory. Now a comparison of the molecular orbital energy levels and the energy of the pi to pi star. So when we have C13-butadiene and ethylene, so we are comparing these two together, where this is not conjugated and this one is conjugated system. So in ethylene we have 2 carbons and 2 electrons in the ground state, and the 2p orbitals gives rise to pi star transition, and when these electrons absorb energy they go into the excited state, right? Whereas in 1,3-butadiene we have 2 double bonds, they are in conjugation with each other. By the way, if you do not understand what is conjugation, then please have a look at my video about the resonance on my YouTube channel, where I have made video about resonance. So this is 1,3-butadiene, psi1 and psi2, and pi to pi star transitions goes to psi3 and psi4. So 4 carbons at the ground state and then 4 p orbitals. So this is the energy level difference, and this is how we can explain that why 1,3-butadiene absorbs at higher wavelength compared to the ethylene. Okay, the energy gap dividing the bonding and anti-bonding orbitals becomes progressively smaller with increasing conjugation. Figure 7.13. This one plots the molecular orbital energy levels of several conjugated polyenes. Again, polyenes means having many double bonds of increasing chain length on a common energy scale. Arrows indicate the homo-LOMO transitions. The increased conjugation shifts the observed wavelength of the absorption to higher values. In a qualitatively similar fashion, many Auxochromes exert their bathochromic shifts by means of an extension of the length of the conjugated system. The strongest Auxochromes invariably possess a pair of unshared electrons on the atom attached to the double-bonded system. Resonance interaction of this lone pair with the double bond increase the length of conjugated systems. For example, this is any atom B which possesses free lone pair of electrons, and these free lone pair of electrons are in conjugation with the double bond, and this is how we can show the conjugation through resonance bonds. As a result of this interaction, as just shown, the non-bonded electrons become part of the pi system of molecular orbitals, increasing its length by 1 extra orbital. Figure 7.14 depicts depicts this interaction for ethylene and an unspecified atom B with an unshared electron pair. However, any of the typical Auxochromes groups are OH, OR, X, or NH2 could have been illustrated specifically. In the new system, the transition from the highest occupied orbital psi2 to the anti-bonding orbital psi3 always has lower energy than the pi to pi star transition would have in the system without the interaction. Although molecular orbital theory can explain this general result, it is beyond the scope of this book. The book is the Introduction of Spectroscopy by Pavia. So this is the energy diagram. On the y-axis, this is ethylene, butadiene, hexatriene, and octatriene. So we have 1 double bond, we have 2 double bonds, 3 double bonds, and 4 double bonds. 4 and 3, 2 and 1 double bond. So as you see here in the one, the energy gap is larger. There is isolation system. So this is for ethylene. Whereas if you see the butadiene, the energy difference becomes smaller. And for hexatriene, the energy difference even become much smaller compared to butadiene. Whereas if you look at the octatriene, the energy difference becomes very smaller. So the energy difference for octatriene is smallest. Hence, octatriene is going to have the highest wavelength. Hexatriene, the energy difference is smaller. Hence, it is going to have a higher wavelength than butadiene. Butadiene is going to have a higher wavelength than ethylene because it has 2 double bonds. They are in conjugation. And ethylene is going to have the minimum wavelength because the energy gap between the ethylene orbitals is highest. This is how the effect of conjugation takes place upon the alkenes. So there are higher the number of double bonds, higher will be the wavelength. Ultraviolet spectroscopy. So energy relationships of the new molecular orbitals and the interacting pi system and its auxochrome. Molecular orbitals of resonance system, psi1, non-bonding electrons on B, ethylene, pi goes to pi star, double bond, and then we have psi2 and psi3. This is the system. These are the electrons which are involved in the conjugation. As a result, energy becomes smaller and the wavelength becomes higher. In a similar fashion, methyl groups also produce a bathochromic shift. However, as methyl groups do not have unshared electrons, the interaction is thought to result from an overlap of the CH bonding orbitals with pi electron system as follows. So this is how methyl groups contribute towards the bathochromic shift. This type of interaction is often called hyperconjugation. Its net effect is an extension of the pi system. It also, methyl groups contributes towards the bathochromic shift, increases the wavelength maximum of the molecule through hyperconjugation effect. And that's it. That was the effect of conjugation from this video. If you haven't learned anything, or if you are still unclear what is the effect of conjugation, then please drop down your comments in the video below, then I'll try to get back to you. Once again, thank you for subscribing and thanks for listening. Take care. Goodbye. See you.